Okay, so this is our final paper for the quiz, and we'll just be reviewing some of the questions which were shared in the group. So the first question which was shared, this was shared by Casey. So it was this question here. And from this question, the interesting questions that I observed or noticed were C here. C was interesting, and also B. Everything else seems ordinary, so I will leave the ordinary ones for you guys to try. So let me start with C. And for C, we have R sine theta being equal to ln. We have ln R plus ln, this is ln of cos theta. So this is what we have for question C here. Now, how do you answer this one? So let's look at it. So for this one, the logic is very simple. You know to say that firstly, based on a right-angled triangle, for an angle theta, r being here, x being here, and y being here, you know to say 1 r is equals to x squared plus y squared, and then these are under the square root. Secondly, you know to say by SOHCAHTOA, x will be equals to r cos theta, and y will be equals to r sine theta. So these are going to be some of the key things that you want to take advantage of. There are more that we can use, but I think for this question, this should be enough. But perhaps before we go far, this one, for example, can be identified. You see that that is r sine theta, and r sine theta is y. So already this can be rewritten so that the left-hand side is now just a y. But now we see that the right-hand side still has a theta somewhere. So we don't want to have that theta. We don't want to have that r. Everything has to be rewritten so that the equation shows up in terms of x and y. So how do we do that? Well, the r and the theta here are separate. So, but we observe that we do have a log here. So what should come to your mind here are properties of natural logs or log functions. And one property in particular that is going to be useful here is if you had log ln A multiplying ln B, you should understand to say that this will be the same as ln A plus ln B. So this is one property of natural logs. So based on this property, you see to say that this is ln R plus, so the key thing is this is an addition, plus ln of cos theta. So it's like they are giving us the right-hand side of this property, where this is ln R, or A is R, plus, and this is ln B, or in other words, B is cos theta. Working backwards, it must mean that this was initially ln A becomes R, and then B is cos theta. So it reduces to this form. So the right-hand side here can now be written as ln of R cos theta. So ln of R cos theta, guess what? Another expression we can relate to the Cartesian has showed up. When you come back here, you see that it is this one. R cos theta is x. So that our expression now can be written as y is equals to ln x. So if you want, you can even put the modulus because ln does not take negative arguments. So this becomes the Cartesian form of that expression which they gave us. So this is what we have. This becomes the final solution. So if you're going to sketch this, of course, you're just sketching the graph of y is equals to ln x, and you know how that graph goes. So that's the graph of y is equals to ln x. Okay, so the key part was just getting that expression. So it's saying describe the graph. So identify, we have found that's a linear expression. In terms of how it goes, in case you are wondering how that graph goes, something like this. For natural logs, you know to say when the argument here is a 1, then the answer here is going to be a 0. But you know to say you never have negative values of x, it will be undefined. So this one goes more like this. It never cuts the y-axis, so the y-axis will be an asymptote. So this is how this graph is going to go. This is going to be at 1. So this is how it goes. And here we have a y. So let's quickly go to the next one. This we're going to leave it here. And let's see if we have a question on this one. Do we have any questions on that one? Okay, looks like we're okay. So let's look at B there. How do we approach B? So again, B quite interesting because it doesn't directly resolve. It requires you to see one more trick there. But what do we see? Again, let me start by reminding you of the relations between polar and rectangular. For this being theta, x being here, y being here, r being here, just like as we saw before, r is going to be equals to x squared plus y squared. And then apart from this, you have x is equals to, this is going to be r cos theta, and then you have y is equals to r sine theta. But notice that one more relationship can be defined here, and that is if you tried to look at it in terms of tan. Notice that if you tried to get tan theta, you're going to end up with y over x. This is what makes this question interesting, because you rarely use tan. Most of the operations you see will use this, this, and this, but they rarely bring out tan. But for this one, we see that tan is going to be key here. So how are we going to work it out? Well, first I'll resolve the sec there. This becomes 4. I'll keep the tan exactly the way it is, but the sec becomes 1 over cos theta. From here, I can cross multiply that cos, so that now I have r cos theta being equal to 4 tan theta. Now my expression looks like this. Well, it becomes straightforward at this point. R cos is here, can be replaced with x. Now tan, we see that tan is what? Y over x. So that this becomes 4, then we have y over x, where we have tan theta. So that now our expression just becomes, we can say x squared is equals to 4y. And we're done. When you look at this, this is a parabola. We can, from this, of course, we can conclude by finding the directrix of the parabola, because this has a general equation of 4py. So you can easily find where the directrix is. You can easily sketch the parabola. I think we've done lots of parabolas before. So hope you guys can easily finish it from here. Are we okay? Any questions from here? Okay.